good day everyone. Today we are again going to construct some conic sections, but this time by paper folding. So it's going to be a little bit different. Now we'll consider all four: circle, ellipse, hyperbola and parabola. Parabola is slightly different, but in the rest of them what we shall be doing is we shall be given a circle. So we shall be given a circle and the center. These are given. So naturally we know the radius. Everywhere it will be the same. Then we shall be given one point in the plane of the circle, but it may not be the same everywhere. It will have different positions in the three different conics. For the circle it will be at the center. For the ellipse the point P will be inside the circle, and for a hyperbola the point P will be outside the circle. We said except for this point of difference, there are other things that are going to be common, and we note down the notations that we are going to use. We shall be folding, we shall be taking points on the circle, and the more points we take, the better curve we shall have. I will show you here. We have taken points very closely here, so we get a good shape, but not very closely here, and therefore the shape here is not very good. So the closer the points we take, the better it is. But for each point on the circle, it may be P1, P2, P96, anything, we shall call it PK. Now, we are already given a point P. We take the point P and fold it so that P falls exactly on PK. P falls on PK and take the fold. What we are going to, the notation that we shall use is that the points on the circle will be P1, P2, PK. After folding, we shall get a crease. This is the crease I have drawn here, the crease, so you can see. We shall call it LK. L is for the line. Corresponding to the point PK, we get the crease line L, which is LK. And the point where the center cuts PK, the point we started with PK, that point where it cuts the crease, that point we shall call AK. Here also, for example, the point P is here. We fold it so that it coincides with PK. This is the crease, that is our LK, where PKO, here OPK, where OPK cuts the crease, that point is AK. Okay, with so much of the notations, we start with the circle. For a circle, what we do is, we take a point P on the center. And so what happens is, that if you take a point P, this is a point, I have taken several points. If we take a point P1 here, and let it coincide with this circle, with the center P. Now P is at O, O is the center. This has coincided, and this is the fold, and that fold we have called P1, or rather L1. This is L1 corresponding to the point P1 when it coincides with P. Now, the point where OP1 cuts L1, I hope you remember, OPK cuts the crease. That point we call AK. Here I have taken P1, so A1. If I take P6, then on corresponding L6 I will get A6, and so on. And now we show that this point is on a circle. This point for any position, whether you take P1, P2, P6, P10 and get A1, A2, A10, whatever, all these points will lie on a circle whose center is O and radius is 1/2 r, if the given radius is r. How? Well, we shall note that this will always happen when we fold. P falls on P1, here is your AK, so the crease or the fold always bisects PP1, so PA1 is A1 P1. In fact, it is the perpendicular bisector of PP1 or PPK. Then, naturally, we are looking for PA1. How much is PA1? That is half of PP1, and that is half of R. So the distance from A1 from O or P is half of R or R by 2, and that is for any position of A, and therefore A1 lies on a circle whose center is O and radius is R by 2. And this is what we get when the points are closer. You get a shape that is closer to a circle. Here there are many more lines missing. Ultimately, if we draw, we shall get a circle. And over to ellipse now. For the ellipse, we have already seen the point is inside. We let it coincide with PK. Here is the crease, and the crease cuts OPK at AK. This is for one point. When you take several points, P1, P2, P3, and these are close by, these are a little far, so you will see that where these lines go, you will get a closer curve or a better curve, and here it's not that sharp. But this is how when we take more points we shall get. Now for this is P, this is P6, P1, P2, P3, P6. We coincide it with P, we get the line fold LX. On LX, where O, on LX, where OPX cuts the line LX or the fold AX, we take AX. That is exactly what we have done here. And for showing, now it's not enough to say that AK lies on an ellipse. We have to show that it actually lies on an ellipse. And in order to show that, I take this simple, where there are not too many lines. The point inside the circle, a point on the circle, P coincides with PK, LK is the fold, and OPK cuts the fold in AK. I just repeated it. We want to show that AK lies on an ellipse, not any ellipse. Whatever your A1, A2, AK, A10, they will all lie on an ellipse whose foci are O and P, and the constant distance between, or the major axis, will be equal to R. Let's see how. If this AK is to lie on the ellipse, we use the property we use for string construction. We must show that OAK plus AKP is constant, if we want to show that O and P are foci. Now when we fold, you can see that P falls on PK, so the whole of AKP and AKPK will fall on each other. And therefore, AKP is the same as AKPK in length. Now we want to show that PAK plus AKO is how much? Well, this is equal to that, so it is equal to PKAK plus AKO, and that is PKO, which is R. So OAK plus AKP is R, which is the radius of the circle. So that's the major axis of our ellipse. The foci will be O and P, and all the A's will lie on that ellipse. Now over to hyperbola. For hyperbola, we do the same thing. Same means almost the same as this. We take any point P outside, that's given. Now every time we take different P's on the circle, let P fall on PK, fold, that is our LK, and where the crease cuts, here we saw OPK. This is OPK, here the crease is below, so the point is below O, there it was above. And now we want to show that AK is a point on the hyperbola. Which hyperbola? The hyperbola whose foci are O and P. In that case, we must show again what we did for string construction, the difference of the distance of AK from P and O. The positive distance should be constant. Let us see now. Before we start, we want PAK minus AKO. But as we saw earlier, when we fold from here, you can see that as P goes on PK, AKPK is the same as AKP, the length. And therefore, we want PAK which is equal to PKAK. So, PAK plus AKO is PK, we want minus, I was wondering how, minus. PAK minus AKO will be PKAK minus AKO, and that will be the length r, OPK. That's the length r. So for any position of AK, wherever you take PK, you will have different AKs, and every time PAK minus PAKO will be r. So that the point will lie on a hyperbola. Okay, now over to the parabola. Parabola is slightly different in the sense that there we were given a point and a circle. Now we are given a point P and a line L. The blue is what is given to us. The point P and the line L. What we did there was we took a point for ellipse and hyperbola, any point on the circle, and P1, P2, P3 and so on, all different points, as many as you can. Call one of them, take one of them, say PK. That point should fall on P when you fold. So now I have taken any PK and I let it go over to P, and what we get is our fold, and that fold we shall call LK because it corresponds to the point PK. Now our AK has to be on the crease, but there is no OP like ellipse or hyperbola. So we get AK in a slightly different way. What we do is, we started with the point PK, one of the points. At that point, you take the line, you have the line L, draw a perpendicular to the line L at the point PK, and this point where it cuts the crease or the fold, as you can see, that point will be A. Now, we claim now that this AK will lie on a parabola whose focus is P and directrix is L. Or in other words, what must happen is that if this is to be a point, PAK must be equal to PKAK, the distance from the focus, distance from the directrix. Now, we make sure that this will happen for every case. This is the general with more points. This is the line L, the point P, and we have taken P1, P2, P3, P9, not necessarily equidistant as you can see. And for each point, for example, we have taken P, it falls with P1, and this is our line or the fold L1. So similarly L2, L3 and so on. For all 9 we have got the creases. I have drawn it with pen, and you can see that it gives you the shape of a parabola. But that's not enough. We have to prove that it's a parabola, and for that purpose what we are doing is this. I'll show you exactly what we did here. We take any point PK and take a perpendicular to the L at the point PK till you hit the crease. For example, suppose I take the point P6. I know that my line L6 is here. So I draw a perpendicular from P6 up to L6, and where it cuts it, I will call it A6. And in that case, A6 is on the parabola. Similarly, we will have A1, A2, A3 and so on. And now we show that it has to be on the parabola because, or in other words, we have to show that AK, the distance from P is equal to the distance from L. We have folded, and as before you see that AK is on the fold, P and PK fall on, the lines, two lines fall on each other. So PAK is equal to PKAK, nothing more to prove. The point is equidistant from a fixed point P and a given fixed line L. So this is the focus, this is the directrix, and that's the parabola. So that's how we get the different conics. Well, thank you.